Hello friends, welcome to Unacademy, which is the largest online education platform for GATE, Computer Science and Information Technology. In this session, I'll be talking about the finite automata with output and also pumping lemma for regular languages. So these two topics are not much important for exam, but there were questions and once in a while they might ask in exam, and they were asked already, but it's not that much important compared to other topics of the regular languages. So I want you to focus less but practice also less, but have a clarity in the concepts. Why do we use the finite automata with output? And they will be giving a machine to you, and you require to understand, you need to understand what kind of functionality happens with a given machine. And pumping lemma is also the questions which are very less, but I have seen two questions in the so far 30 years that questions are also very easy to understand. So let me introduce myself before starting today's session, guys. Okay, myself is Mallesham Devasane. I'm working as an educator on Unacademy in the segment of GATE and ESE for computer science and IT engineering students. And my referral code DEVALIVE, you want to use anytime to access the free classes or paid classes, you can use DEVALIVE as referral code. And this is my profile where you can access all my classes on Unacademy. So unacademy.com/DevaGateCSE. And if you want to know about me, I worked various institutes in India which are premier institutes, and I've completed MTech from IIT Bombay. Then I started taking the classes for GATE, and almost I have 12 years of experience. And if you look at Unacademy, which are paid courses I'm talking about, the popular courses that I have taken: C, TOC, Compiler Design. And this is my referral code. You can remember very easily, DEVALIVE. DEVALIVE is also eligible to get a 10% discount. Also, you can access all my classes freely. Free classes you can access, and also you can get a guidance whenever you want to take the subscription, and I can help you to crack the exam with the support. Okay, so what are the benefits you have through the plus? You will have a live classes from any educator on Unacademy in the same segment of GATE and ESE, and crash courses and rank batches. Any courses that we launch are completely free, and weekly test, doubt solving sessions, and you can ask the doubts in English and Hindi, and you can look at the courses both in English and Hindi. And iconic, all the benefits of plus: personal coach, planner, booster, and analysis of every test, and separate study material, and many more. One-to-one interaction with every educator. And these are my classes on Unacademy, where nearly you can see that nearly 400 classes till date that I have taken on Unacademy. So you can access those classes freely by visiting unacademy.com/DevaGateCSE. Okay, so if anybody not aware of how to use the Unacademy platform, please visit www.unacademy.com, or you can download Unacademy Learners app, Unacademy Learners app. You can log in, and whenever you require the code, you can use DEVALIVE and choose the GATE and ESE, and you can search any educator to access the videos, right? And if you want to take the subscription, you click on subscription, and you will be redirected to two subscription plans, plus or iconic. So iconic, as just told, and you will get the plan for plus and iconic. So it is your choice, plus or iconic. So if you click on iconic, then you will redirect to iconic subscription plans. If you click on plus, you will be redirected to plus subscription plans. So you might ask, sir, why do I take the plus and iconic subscription? Look at the educators who are working on Unacademy, and you are eligible to learn from top educators from India, and all these people are top educators and who are working on Unacademy. You are eligible to access any course from these educators, and many more are there on Unacademy. So this is the advantage, where you don't have any limitation how many courses you want to learn and how many times you want to learn within the given period of time. So that is the advantage of using DEVALIVE referral code, and you can access any course from any educator freely, completely. So what are the benefits that I am talking about? Structured courses, multiple courses for the same subject, study as per your interest, learn from the top educator, study with proper planning, and enjoy learning by gaining the confidence day by day, an unimaginable journey throughout your preparation, guys. And that's what, when you click on plus, you will be redirected to this plans, and you can choose any plan which are popular, 1.5 year, 2 years, and these are the plans for 1.5 year, 2 years price, and choose the referral code DEVALIVE. Do not forget that. And another one, iconic plan, which are 1 and 2 years, very popular, and you can choose DEVALIVE referral code. You can see the total amount for 1 year, 2 year. So the advantages are plenty, and you are preparing seriously, then that is recommended to take the subscription. All right. Yeah, good evening Mega and Vedant. Good evening. Yeah, sorry guys, I'm a little bit late in responding chat because I can't see the chat very quickly. All right, Samir, good evening. Yeah, Jatin, good evening. Vedant, yeah, mostly next Saturday I will plan Vedant. 50 questions, yes. Good evening, Jansri. And on this channel you have access to every course that is there in the syllabus, and most of the courses we have completed, and some of the courses are going to come by this month. This month, I think next month we are going to complete even entire syllabus, and 60% 60 to 70% syllabus already completed on this platform. So you can access every video which is available on this channel. Yeah, good evening Arya, welcome back. And guys, we are looking at now, sorry, I'm very sorry, I will look at it. Is this proper slide? Yeah, so this was a mistake anyhow. Theory of computation is our course name. Okay, in this theory of computation, in the previous sessions we have seen regular expressions, finite automata, and regular grammars, identifying regulars, closure properties. So these are the topics we have completed, and this is the maximum weightage in the exam. And the practice we have seen for regular expression, and we are going to practice this one in the coming weekend, guys. Coming Sat and Sunday, we are going to see the maximum practice. So stay tuned to this YouTube channel. Maximum practice we are going to do for this remaining 4 topics, and you do not worry about the questions, the number of questions. You will get practice if you are following my classes, and I will guarantee that you will get more practice from these topics. Okay, but every basic will be completed. Also the minimum requirement will be completed to the practice in weekends. Yeah, good evening Shubhasri. Yeah, all right. And in this session, what I am going to plan, which are finite automata with output. But as I said, this is slightly related to the digital logic, but still we will understand as it is part of the TOC and pumping lemma for regular languages. So I can give the first more priority to the pumping lemma, as the last year they have asked one question, and finite automata with output, which was also asked 2 to 3 times in the gate. So both will have, if you look at the previous years, every 10 years one question was there. So that is the reason you study more, you study these topics, but you do not require much practice compared to other topics. So every time I was explaining, I was also giving the importance of that topic. Remember that. So you can prepare the similar way, learn properly and practice as per the requirement. All right. Good evening Bharat. Good evening Anurag. Yeah, good evening everyone, guys. All right. So let me begin today's session. Very quickly I'm going to talk about, so don't worry much about it. And guys, the finite automata is actually, you know it. Finite automata, we have with output. First we have learned without output, and second one with output. But guys, most of the people, they do not know the behavior of these two machines are different, but the way you design the complexity is equivalent, guys. Without the property of regular, you cannot design, and very less people, they know they are equivalent. They are equivalent in terms of complexity of designing, in terms of the property that you observe. The way that they may be different, because of one has the final states, other will not have the final states. But when you are doing with output, you can also keep the final states if you want it. And do not forget these two kinds of machines in terms of logical, they are equivalent. They are equivalent, remember that. And I can build the machine with the both properties. I need to produce the output and also I want to keep the finals. I can keep in the with output also. So do not forget that. But without output, anyhow the behavior is different. We have designed DFA and NFA earlier, and NFA without epsilon transitions and with epsilon transitions. Okay. And only the problem that you have, why I am writing equivalent at that place, you can write, remember that. Okay, these are equivalent, and you know that this all machines are finite automata. But in with output, you have two types of machines. One is the Murray machine, another one is a Millie machine. And these two are also equivalent. So all these machines are equivalent at the end. Everything you can design here. These two you can design deterministically or non-deterministically, but by default they are DFAs. By default these two machines are DFA. Okay, so this is the first important fact, by default, but you can also design them using non-deterministic nature. Should not forget about that. Okay, now let me talk about the finite automata with output. So this is the concept that I am going to talk about, finite automata with output. Okay, in this finite automata with output, what you have, you will have an input, but some finite automata you may not have input to, like traffic signal. If you look at that, there is no input to them. Input is just power. So you are going to produce the outputs. You will change from one traffic light color, right, one color to other color, and their input is optional. But in general, let's say input is there and output you will produce, like one's complement of a binary number 0 1 1, its complement is 1 0 0, right? If you are looking for one's complement, so where do you use this kind of machines, finite with output? To design the digital circuits, like combinational sequential circuits you have, right? So if you want to implement one's complement, two's complement, adder and subtractor, right? So such even sequence detectors, sequence generators, and this kind of a machine is going to help you to implement such things. Even you can use to produce the tokens of the lexical analyzer, and many more you have. And what is the configuration of finite automata with output? Yeah, if I miss anybody, yeah, Bharat, good evening everyone, guys. Yeah, I'm sorry late. Yeah, good evening. And if you are watching this video, please like the session if you are missing. Okay, and this we have tape. Everybody knows it's a tape, and we have head here, and we have a control. Finite automata, we know it, right? So we have 5 parameters to understand. Okay, you have some machine inside. Let me talk about, this was earlier read head, now it is read head as well as write head, but this is has a limited power, not like the Turing machine. Remember, this is read or write head. You may use same tape or different tape. Here this is input or output tape. Input output, you no need to use the same tape. You can use the different tapes also, but we keep it. If you want to produce the only one output for every input symbol, then you can use the same tape, or for every one input you want to produce 2 symbols as an output, then you need to use the 2 different tapes. Okay, now I have input like 0 1 and 1, and what is your target? You have some diagram here. You will start somewhere and you do something here. Don't worry much about it. So what we have here, the parameters, we are talking about finite automata with output. Yeah. So tell me, when you are looking at without output, we have a Q, sigma, delta, Q naught, F was there. Now F is optional. F is not compulsory because we are not looking at F. So instead of F, we have 2 parameters. One is delta, other is lambda. Is it clear? Because our final state we don't keep here, we don't require here. If somebody keeps, ignore them if you don't want. but some of the machines are there, you might require final state, guys. You might require. Some people want to know, they want to produce ones complement of given number when they detect double one inside a number. Look at that. I'm writing, guys. You might need the knowledge of something like that, right? When they detect double one and they can go to final state and they keep on producing ones complement. So it's a very interesting problem, that is, you need to recognize your input as well as you want to produce an output. You may need a final state if you want. Okay. Now don't worry much about it. You can keep the final state if you require, otherwise not. So by default we don't need to keep it. Now this delta is called as output alphabet. Why do you require output alphabet? Already input is there. Because sometimes the output alphabet may be different from input alphabet. Example, here ones complement is same, but some people might need 0, they want to replace with a. Instead of ones complement, I want to implement a different machine for me, that is, every 0 I want to replace with a, and every 1 I want to replace with b, then a, b, b. So 0 replace with a, 1 replace with b, this is my machine. Then 0 replace with a, 1 replace with b. Then here sigma is 0 comma 1, but delta is a comma b. Delta is a comma b, guys. Everybody, so this is the most important fact. The output alphabet need not be same as input alphabet, so we require to maintain two alphabets to understand the machine configuration. And delta, everybody knows, this is a transition function. As I told, this machine by default DFA, so we use the same DFA definition, q cross sigma to q. This is a DFA definition because these two machines by default DFA only. By default it is DFA, but it is two types. One is the Murray machine, another one is a Mallesham machine. And we are going to talk about here, lambda is different for them. How do you produce the output is different for them. Lambda is called as output function, guys. Lambda is the new parameter for you. This is important, and this is going to differentiate both of them. This is called as output function. Output function. Is it clear? If anything is difference that you see from Murray machine and Mallesham machine is going to be the output function. Clear? Q is the same set of states. There is no change like normal finite automata that you have seen without output. Yes. Come on, guys, keep liking, please like the session if you have not liked it. Thank you so much. Now, how do you understand these machines? As I told, I want to understand these two machines. Then first you should learn what is the output function of these two machines. Anyhow, both are deterministic machines. Like a DFA, you can say both are DFA, but output function for this machine and this machine is different. Here, output is calculated by looking at the state. Output is associated with a state, right? So this is Q. When you look at the Q, you will get the output. So this is output alphabet, this is the state. So states and output symbols, and whenever you reach the state, you will get the output. So we'll see that the difference. And output function in the Mallesham is output associated with a transition. Then what is the transition? Output associated with a transition. And what is the transition? You know that Q cross sigma. So Q cross sigma is basically a transition. This is your delta all the time. That will be talking about a delta. So you should know what is the transition. Then you will know what is the output. So output is associated with transition. So when you look at these two machines, this machine, if it is a state, guys, if it is a state, let's say Q naught, then output you can keep inside. Like you might want to produce small a. This is the output. This output you can keep inside or outside, but that small a should be associated with the circle. And here Q naught is a state name, let's say, example I am trying to provide. And when you have a transition, let's say A is the transition, then who is the transition? This is a transition, so where outputs are not small a. Let me take some other input, sorry guys. Okay, take 0 as your input, and who is the output? A is the output. So this is output here. Output is associated with transition q0 comma 0 together. Here I can say that lambda of q0 comma 0 is equal to A. So this is output. Okay, output is associated with transition now. Q cross sigma is a transition here. Okay, this is the main difference. This is the main difference between the Murray machine and Millie machine. Whoever can understand the Murray machine, they can also convert to Millie machine, because these two machines are equivalent at the end. And also remember, these two machines are equivalent because you can convert one to other. We have an algorithm guys. So let's start with one example to understand both of them. Okay, so one small example guys, okay, focus on small example. Okay, this is the q0 and this is the q1. Okay, just to avoid this names, let me take some other names, small p small q, that looks easy for me to refer. And now I just told you I want this kind of machine. What kind of machine? If I give you 0 double 1, I want to produce A double B. Then what I do is I do something, don't worry much about it. Small a, small b. And that small a, small b you can keep outside also, but keep with a state. And when 0 comes, I want to produce A. When 1 comes, I want to produce a B. And here also same procedure. 1 comes, I want to produce a B, and 0. Don't design. Just look at, I am taking my own example. Then how do you understand it? Now look at this machine, the configuration. Who is the initial state? P is initial state. And what you are actually reading from P, 0 double 1 you are reading guys. If you read 0 double 1, definitely you will halt at Q only. And doesn't matter which state you halt at. Right, after reading 0 double 1, you can look at that 0 and 1, again 1, you will halt at Q only. But how this is going to work? Look at, from P you read a 0, you will go to P, and I will read a 1, you will go to Q, you will read a 1, you will go to Q. But what happens here? When you reach a P, A produced. When you reach a P, A produced. When you reach a Q, B produced, because output associated with a state guys. So what is the output produced? For the 0 double 1 is actually different than you are expecting. This machine. Now look at guys. Look at what's happening. Right? So this is your machine. What you are actually giving to this machine and what you are actually getting from this machine. Everybody, you are actually giving to this machine is 0 double 1, but what are you getting from this machine? A, B, B. Now here, what you need to focus, this first symbol is ignored all the time. Ignored every time. Why? Because that is produced without reading an input. Everybody, so when you read a 0, A will be produced. When you read a 1, B will be produced. When you read a 1, B will be produced. So actually it is considered as A double B is the actual output we need to ignore. We need to consider. So required output, it's not actual, it's a required output. So this is the required output. Actual was double A double B we got, but we want just accept the first output guys. Is that clear? So this is the behavior of the Murray machine, where the first output associated with the initial state is ignored all the time, because when you begin the machine, automatically output produces. It's just like a traffic light. You know, when you switch on the traffic light complete circuit, automatically it starts from something. So you will ignore that, but you will start from the next state. Okay, same way. And of course you can also reset, that depends on your choice. Okay, now let me help you. Millie machine, sorry, again I copied it. Okay, this is the Millie machine. So what is the Millie machine? And I'm taking something, don't worry much about it. Okay, let me take something where I want to use some other names. X. x 0 I produce 1, and okay, 0 I produce A, 1 I produce B. Now look at guys, if you read same thing 0 1 1, what happens now? Guess the output now. Now read the same one 0. Give an input. Now tell me what is the output you get. Quick. Give 0 1 1 and output is A double B. A double B. Then how did you get that? Yeah, I shy. How did you get that? So now look at the x. When you read 0, you will go to x. When you read 1, you will go to x. All the time you will go to x. But the output immediately produced, guys, because 0 output is A, 1 output is B. So immediately produced because it is associated with transition. It's associated with transition, guys. So they don't take much time to produce the output because output associated with the transition. So output is A double B. And if you give n length input, that's 3 length, you got n length output. But is this always true? That I'm going to help you. Everybody? Yeah. Yeah. Is this always, some people remember the formula but they don't understand the concept. Is it always correct? Let me help you. Okay, before solving any problem, let me help you guys. Suppose my input is like, let me help you guys. And here 0, I want to produce double A, 1 I want to produce double B. Then if I give 0 double 1, what is the output produced? This is my functionality. I want to replace 0 with double A, I want to replace 1 with double B. Then what do you get? If it is the Mallesham machine, then initial state, let's say it produces double A, let's say this is the default. Assume that either double B, it's your choice. I don't know what is that exactly. It depends on your machine. So every 0, now 0 you read it double A, and 1 you read double B, and 1 you read double B. So now what is the length, guys? It's not n length. If this is n length, it might be producing how much length? 2n plus 2, and plus 2 is extra here associated with initial. This may be plus 3 if depends on your initial state. Yeah. And if it is a Mallesham machine, then 0 double 1 definitely produces double A, double B, double B. Then it is a 2n length. If it is n length input, 2n length output. But this all depends on the configuration of the machine. Don't decide blindly n length input is n length output. No, guys. It has to depend on what kind of problem you are solving, right? So some people have, I have seen, they try to remember n length input, n length output, n length input, n plus 1 length output. That's a wrong approach, guys. That's a wrong approach. You will look at one more example I am giving to make you confidence in this kind of behavior. Now look at 0, I may produce double A, 1 I may produce triple B. It's my choice. How do I want to produce? Now here if I give a 0 double 1, if I am going for a Mallesham machine, how difficult it is, guys. The first you don't know default, it might be double A or double B because you don't know which output is associated with initial state, and later on 0 double A, 1 triple B, and now creating the formula is not easy, guys. And if it is n length, don't say that is 2n or n plus 1 or 2n plus 2, which is not going to work. Are you clear? This output length can be it is 2 3 3 how much 8 is correct. 8 plus 2 or 8 plus 3, it may be 10 or 11. It depends on what output is the initial state. We don't know this one at all. It's all depends on behavior of the machine, guys. So do not follow the formulas in terms of some textbooks. I have seen such questions from many resources. They keep on asking the question directly without giving the configuration of the machine, and I have never seen such questions in the GATE exam, right? So I have a clarity with the given data. You can analyze what answer it is. Now if it is n length, it will not work with n plus 1, it will not work with 2n plus 2. Is it clear? So this is going to be a different answer, and I want you to understand clearly Moore and Millie Machine. So let's start without wasting our time, guys. Yeah, please like this session if you are watching this video, and we are beginning this session now. And before this, let me help you. What is these two machines? Moore machine and Millie machine. Yeah. Okay, in the beginning of my learning, people used to write anything, a Millie machine, and guys, this is wrong, right? So you know it. What is that spelling? It's a scientist name. It's a Millie machine. Remember that. Fine. Now the first point, it is by default DFA. That doesn't mean that you can't construct NFA, guys. You can do that. One time I have seen one question in TIFR, they have used non-deterministic machine for this with output. It is by default, but you can design even NFA also. You can change the configuration later. It is by default DFA, both of them. It is by default DFA. That is the reason the delta for both is same. Q cross sigma derives a Q by default. Second, here output associated with state. So you can keep inside the state or outside the state, but you should keep with the state. Like, inside you can keep A, or you can keep outside, doesn't matter, but keep with the state. If this is a state Q0, and you can keep that small a is an output, small a is an output that you can keep either in or out, but associate with a state. And no need to write here, you can mention in the data, given data also. So here lambda nothing but, if you have a state, you can see the output, and this one output is associated with a transition. So you must know what is the transition every time. So what is the transition? You know that Q cross sigma is your transition, so lambda depends on that. So if you have, let's say Q0 is a state, then if you have an input, maybe 0 is an input, let's say, then you may produce A, right? So this is the most important one for the Millie machine. Okay, now what is the length of the output produced? That depends on the given configuration. If every symbol I am producing one length output, then definitely you can compare both. Okay. These are the two important facts. Final states are optional. Final states no need to present in the machine, right? You can ignore them all the time. Now let's begin the machine. Okay, let's begin the machine, guys. Okay, one's complement of a binary number. One's complement of a binary number. Have you seen how easy to understand? But in the exam, you don't construct it. They will give you a machine. You should be in a position to answer it. Just now, the configuration is must. Before that, your assumptions are important. So if input is 0, 1, 1, what is the output? I just told. What is the output? You are expecting 1, 0, 0. And what output will be produced? Definitely 1, 0, 0. But Moore machine will produce by default some output, and Millie machine exactly will produce 1, 0, 0. So do not worry about the default output produced by the initial state. So if you are designing a Moore machine, slightly configuration changes, and Millie machine configuration changes slightly. Okay. Yeah. Now if you are looking at how many different outputs are there, here delta is 0, 1, and here sigma is 0, 1, and two different outputs here, guys. At least two states required, at least two, remember that, because one state associates with 0. Okay, so I'm sorry, one state output is 0, other state output is 1. You can say that this is a capital A or capital B state. and at least 2 states. I don't know more than 2 or not, that depends on the problem, because I have 2 different outputs, minimum 2 different outputs. So Murray machine will guarantee 2 different output symbols are there. 2 different output symbols are there. Implies minimum 2 states required in Moore machine. Minimum 2 states in Moore machine or Murray machine. And Milli machine, it depends on the problem, guys. One or more you can say. Milli machine is not going to depend on how many outputs you have. You might design this problem using just 1 state. Okay, let's talk about this. And who is the initial state? You decide. If you want the initial output is 0, then keep capital A is the initial state. If you want the initial output is a 1, you can keep the B is the initial. Initial is your choice. There is no restriction on initial state. So I'm keeping A is the initial, that's okay. And if, guys, input, I'm talking about input, if 0 comes, I go to 1 because I need to produce a 1 for the 0. And if 1 comes, I will stay here itself because I need to produce a 0 for 1. So that's a capital A, because you need to make a DFA. That's why every 0, 1 I have to think from every state. And from the capital B, again 0, 1 you have to think. If capital B 0 comes, you want output 1, so come to the same state. If you get a 0, opposite, right? You want opposite. I'm sorry for that. If you get a 0, stay here because output you want 1. And if you get a 1, go to other state because that output is 0. And this is going to do 1's complement of a binary number. But one output will be produced extra, either 0 or 1, that decided based on your choice. Ignore the first output. Ignore in a Murray machine. In Milli machine, the output is just 1, 0, 0. And look at now. And this is, let's say, P is your state. If 0 comes, produce 1 directly. And if 1 comes as an input, produce 0 as an output. So this is pretty straightforward, right? So if you have a 0, 1, 1, it produces 1, 0, 0. There is no default output. Here, without reading an input, output never produces in the Milli machine. And Milli machine, the output is very quick, guys. If you compare the previous 2 logics, you can look at that. Previous 2, where is that? This one. Not this one. Sorry, guys. This one. You can look at this. The output, input you are reading here, but output produced here. But if you look at the machine, the input you are reading here, output produced immediately. So these are the Milli machines are faster in producing the outputs compared to a Murray machine. A Murray machine basically will works based on positive edge triggered, negative edge triggered, right? But Milli machine, it's throughout the clock. At any time there is a change, immediately output is affected in the Milli machine. If you know about clock circuits, you can easily compare both a Murray machine and Milli machine. So in digital logic, you might understand what is the positive edge triggered, negative edge triggered, or level triggered, right? So the Milli machine is going to look at throughout the clock, wherever change happens, immediately output will be affected. But in Murray machine, only the change happens at a particular case, either positive edge or negative edge triggered, depends on the machine. Okay, output produced with some delay in the Murray machine. Okay, which is the better? That depends on the problem. Both are better, both are having advantages, both are having disadvantages too. Alright, this is about 1's complement, guys. Now 2's complement of binary number. 2's complement. So I am going to implement Milli machine. I will help you how to convert into a Murray machine. So now we should have an idea, guys. Now what kind of idea, guys? Everybody knows what is a 2's complement. Suppose you have this is my number, right? This is input. Then what should be output? Output will be 1's complement plus 1. 1's complement plus 1. That's 1's complement is 1 0 1 0 1 1 plus 1. So you will get 1 1 0 1 carry, again 0 1 carry, and 1 1 0 1 0. This is the 2's complement of a number. This is your output. But guys, you can also do some other way. The whole effect you can do some other way. Everybody knows that other shortcut. This is a method 1. Method 1 requires doing 2 operations, 1's complement and then 1. But there is another way. you take an input, this is your input, and why don't you scan in reverse direction, so that look for the first one, till the first one you keep same, that's 100. Look at that, do you have the same? After that you need to do the ones complement. What do you get? 101. Is this same or not? What we do, search for first one in reverse from LSB, and till that one copy as it is, but here do ones complement. This is another logic to get the twos complement. Most of you have learned, might be in digital logic, guys. Then how do you implement the machine is slightly difficult. Look at, guys, the input, what do you give? You need to scan in reverse direction, right? You need to scan in reverse direction, but can you do that directly? No. So what do? Actual input is 0 1 0 1 00, but what you do is you do reverse manually. So you are going to do 0 0 1 0 1 0. You will give input, give reverse of an input. So this one you give to the machine, and you will scan now from left to right till the first one, and after that you do the ones complement and produce the output as the output is 0 0 1. After that ones complement 1 0 1. So here again do the reverse, then you will get actual output 1 0 1 1 00. This is the actual output now. Clear? But the machine is going to do this much only. This is the machine behavior, and you give the input in reverse order, the output also produced in reverse order, so you do it manually. For that you may use the buffer or some other things to do the reverse. Clear? It takes much time to understand because you need to have assumptions to do the twos complement. Are you clear? So you can use other machines to do the reverse if you want it. Fine. Otherwise, change the machine configuration. Instead of scanning from left to right, do the scanning from right to left. It's also over, right? Yeah. So now how do you do that? Now, what do you do? Output. So first search for the one, right? So any number of zeros, what do you do? Any number of zeros, you keep 0 0 0. So I'm trying to build the Mallesham machine, then I will help you how to convert into a Mallesham machine. So that is easy now. What I do is, any number of zeros, I keep 0 only as an output. When 1 comes, I'll keep 1 only. But after this my logic changes. You can see that forward direction till the first one I keep same. But after that I'm going to do the ones complement. You know ones complement logic, guys? Every 0 we replace with 1, and every 1 we replace with 0. That's all. Automatically halves when the string is over. And this is the twos complement logic. Right? Give the input in reverse order, and once you got the output, assume the output is produced in the reverse order. Right? Now, is this a Mallesham machine? No, right? It's not the Mallesham machine. Now, it is a Mallesham machine. Then how can you convert? Guys, this kind of questions are not important for the exam. Just for have a clarity, because for sometimes semester exams you might require these conversions. So I'm going to help you now. Okay, I'm going to help you now how to convert into the Mallesham machine instead of designing directly. Observe, guys, how many different outputs at every state. Might take much time for beginners. Here look at how many different outputs. Only 0 is the different output. This output, observe output only, not input. And B, look at there are 1 is the output and 0 is the output, and there is another one is the 1 output. You observe only this one, 1 1 0, that's coming to the B, and only 0 coming to the A. So observe the different outputs, that are coming towards a state. So 0 and 1 0, and so depends on that. Observe outputs at every state, output symbols at every state which are coming towards, not going outwards, remember, at every state. So I was observing what are the outputs are coming to that every state. Now only output, and now it means I need to have one state for A. In case if you get 2, if you get it 2 guys, then you can keep anybody's initial, it's your choice. For B, you require 2 states, B0 and B1. Now initial state is A. Now exactly it does same. Now what you have to do, just look at your machine, and you just look at your machine and don't look at output now. Output, it confuses little bit. And look at input. Look at input. A on 0, it goes to A, but output is 0, right? Now on 0 it goes to A. On 1, now this is what the difference is. A on 1, you produce output 1 but go to B. So now this is your output, right? This is your input. So you are going to look at B comma 1 state guys. A on 1, you are going to B comma 1. 1 is input and this one is the output. So match carefully how do you look at the machine. So A on 1, you go to this state because output I want 1. If output is 0 coming, then go to B comma 0. Clear this point? How to get the transition of that A on 1? A on 1 we should go to B, but whichever the B produces 1, you go to that state. Now look at another one, you will understand clearly. Now both are B guys. B on 0 never going to change for both of them. Both of them B on 0 same, but look at this machine. B on 0, it produces 1 is the output. It goes to B but produces the 1. It means B on 0, you have to go to B comma 1. Everybody, so look at this Milli machine and get the Murray machine output. Everybody, now both B states same concept. B on 0, both should do the same job. It's also coming clear, and B also going to there itself, because both B should work same, because both are state B only. On 0 B comma 1, that's all. On 0 B comma 1. Now similarly, help me. For B on 1, it produces 0 and goes to B. It means B on 1, you should go to B comma 0. Both of them do the same job because both are B states only. Both are B states guys. B on 1, both should go to B0. So it's a self loop and other one goes to B0. Anyone, both are state B's only. So this is how we can design the Murray machine. So every Milli machine you can convert to Murray machine. Every Milli machine. But it takes some time because you need to observe the outputs at every state which coming towards that state. And that if different outputs are coming, then you need to create different states. Clear this point? Yeah, thank you Nishu. Great. Yeah. So this is the most important fact for the conversion. I hope you know this kind of questions may not be important, but for understanding the machines, okay, it's important. Now, addition of two binary numbers. Now, here completely you need to assume everything, guys. If you want to produce the addition of two binary numbers, it's not easy at all, guys. Suppose I am giving some number, guys. Okay. And you know 0 plus 0, if you are doing 2 bits, the output is 0. And 0 plus 1, what is it? 1. 1 plus 0, you know 1. 1 plus 1, you get 0, but this produces a carry. Yes or no? And remaining are producing no carry at all. They are producing no carry at all. Yeah. That means you need to remember two things. When I have a carry, how do I? So two cases, guys. Case 1 and case 2. Case 2. Case 1, 0 plus 0, 0 plus 1, 1 plus 0, 1 plus 1. If I don't have a carry, already I am talking about. Previously I have not having any carry because you need to consider there is no carry initially. Yes or no? And this is 0, this is 1, this is 1, and this produces 0 and carry. And no carry. But when do you do this? I am assuming I have no carry previously. I have no carry previous to these two additions. Previous. In case 2, in case if I have already seen the carry, I have a carry already. That means previously you are getting some 1 here. Look at that 1 1 0 and that 1 is coming. You are doing 1 plus 0, but you need to look at this carry also. So that means 0 plus 0 is going to be not a 0, it's a 1, because already I have a carry. Already I have a carry. So 0 plus 0, 0, 0 plus 1 is a 1, and now I produce no carry. I am assuming carry already there. Carry already exists. Remember that. Next, 0 plus 1. Carry already there. 0 plus 1 is 1. 1 plus 1, you have a 0 and you produce a carry. That means 0, 1 and with a carry. This you are adding, but you need to have a carry, right? So you will get a 0 and one more time carry. So this is how you understand here. This is a with carry I am talking about, with carry. And this 0, 1 is different. 0, 1 is we are adding, but I have no carry. This is a no carry previously. Clear this point? Yeah. I am already having the carry here. 1 plus 0, same concept. You will get a 0 and again carry. And 1 plus 1, guys, previously 1 is there. Total 3 ones we are adding. 3 ones. 1 1 you got a 1 0 and you will plus 1 is the 1, again you get a carry. So 1 and carry. And this much information is required to understand addition of 2 bits, guys. Addition of 2 bits. Everybody? So that means especially you require 2 states to understand with carry and without carry. So you are going to maintain 2 states. Without carry, initial state, because initial state always we know without carry. Other state with carry. That means whoever you are reading from with carry state, plus 1 automatically should happen. This is basically plus 0 by default, plus 1 by default. So now from every state, you know, if you are adding 2 numbers, as I told, any number you take, guys. Okay. 0 plus 0, you need to add these 2 numbers. You get a 0 and carry is 0. And next 1 1 is 0 and carry comes as 1. That means from here, how many combinations you have? 0 0, and you have to think about 0 1, you have to think about 1 0, you have to think about 1 1. 4 combinations, guys. From every state we may get 4 combinations. You need to work on 4 combinations. But here the assumptions are very important. This 0 is the first, is 1 bit of the one binary number. This other same position bit of another number. So we are involving 2 numbers at a time, but 1 bit at a time. So that is the concept here. You need to assume all the time what you are trying to add. What you are trying to add. So if you want to add these 2 numbers, how do you give an input, guys? How do you give an input? Let's look at how do you give an input. Okay, any number you take, guys. I keep forgetting that numbers. Okay, some numbers you want to add. So what do you give to your machine? You are going to give 0 0 comma 1 1 comma 0 1 comma 1 0 0 0. How did you get that? Because first you have gathered these 2 inputs, then gathered these 2 inputs, then 0 1, then 1 0, then 1 1. Are you clear this point? These are LSBs of the 2 numbers. Then second 2 power 1 position, then 2 power 2 position, then 2 power 3, and so on. And you are going to give as an input, then you will get output 1 by 1. So this is assumptions. Without assumptions, these machines are difficult to construct, guys. That is the reason most of the people are going to struggle to understand the machines, because they don't look at the data properly which is given in the question. So you must read the question. How do they give an input? How do they observe the output? How many bits they are adding? Everything is important here. Okay. Now if you are doing 0 0, you will get a 0 output, but no carry comes. And next 1 1, you get a 0, but carry comes. And next time 0 1 is the 1, but carry should be added. You will get a 0 and again carry. So this is how it produces, guys. and carry again gave 1 0 is a 1, but again you have a carry plus 1, so you will get a 0 again carry, and this is 0 0. Where did I 4 over, right? 0 0. You had a carry, so 0 0 plus 1 is a 1 is output. So you get output 0 0 0 0 1. This is an output, guys. If you look at the addition, you can see that the output of what you get here. Yes or no? So this is how you produce an output. Yeah. So now let's talk about this 0 0. Is it same state? Is it same state? Yes, no carry. And 0 1 1 0, no carry, but 1 1 you get carry. But what is output? Here produce 0, here produce 0, 1 1. Output is important, guys. I didn't produce output earlier, but I'm doing now. So let me write all the outputs clearly. 0 0 by 0, 0 1 by 1, and 1 0 by 1. Okay, order doesn't matter. 1 1, output is 0, but carry is there, so we go there. 0 plus 0, you know that output has to be 1, no carry, so we go here, but output is 1. I'm producing that. Next, and all of them are producing carry, guys. That means you must stay in the same state. And look at the 0 1 output has 0 0 1, guys. 1 0 output is 0, but carry is there because plus 1 automatically happens, and here 1 1 by 1. So this is how you design a machine, guys. And you need to remember that the state already has the carry, and that is extra. Who will do that? We are designing the machine. So once we design, now you give any binary number, any two binary numbers, this is going to work. But who will design? We are going to design by taking care of this logic. Alright. So this is the most important factor. How do you design these machines are very, very important. Now which machine I have designed? Milli machine. Now you observe, you got every state two different outputs, 0 or 1, right? By looking at this, you can convert to Murray machine if you want it. You can convert this to a Murray machine. Without carry there are two states, with the carry there are two states, with 0 output, with 1 output. Then with 4 states you can design the Murray machine. So I am giving homework to you if you want to practice. But I am trying to help you guys. Okay, this information is very important for you. I have already shown you. Now I am trying to show you something. What I am trying to show you, you can write a table. So let me assume this is a capital A state, this is a capital B state. So how do you design the table here? I have not shown you yet. The table is somewhat complicated, so I am trying to show you. And we have two states, right? We have two states, and one is a state A, other is state B. And here two things. One, you have to look at input. When you read an input, what happens? You have to read an input and you have to look at the next state. You have to get the next state and you have to get the output. Two things, guys. So now let's focus on, you are reading some input. You are reading some input. Like what input you have here? 00, 01, 10, 11. These are the inputs, right? Okay. So let me read 00, 01, 10, 11. These are the inputs I am getting. But what I get a next state, guys. I get two things, a next state as well as output. Next state, output, because every transition associated with output is associated with every transition. So next state, output, A on 00 A, and what is the output you got? 0. And A on 01 is the next state is A, but output is 1. Next state is A, output is 1. Next state is B, output is 0. Is that clear? From A outgoings, and from B outgoings, A is initial state, and from B outgoings, you can see that B on 00, it's coming to A, but output is 1. B on 01, self loop, and remaining all are self loop, but output for this to 0, and for here it is 1. So this is how we design a table. That's what the theory. Rewind the video, Shubhasri. What the state is, you know, right? Because you are carrying your input. If you have a carry, plus 0. This already named it without carrier. After doing everything you are asking back, please rewind the video, right? And that is the reason the people might have problem in understanding the machine, because when I was explaining the theory, without carry, with carry, already explained, right? If you don't get a carry, come to A state. If you get a carry, go to B state. I have clearly mentioned everything, right? I have clearly mentioned without carry 0 0 0 1 1 0 1 1, add it 0 and 1 1 0, but I have assumed without carry, that is from A I was thinking about, other one from B. Both of them I have already written clearly. Please rewind the video, you will understand. Okay, just watch 1 or 2 times, you will get idea. Yeah, come on. So this is how you can construct the table. From A, look at, this is the input, this is the input, this is the output, and next state is there. Self loop means capital A. So this is the next state and this is the output. In general, Shubhasri, you should make your own logic. There is no restriction how do you build a machine, right? Then how do you prepare gate? That you decide how do you want to prepare gate. In general, there is no rule, right? So in general, there is no technique how do you add the two numbers. You should decide how to give an input, how to take an output, because you are designing this machine. Okay. You should have a practice. It's not easy, that's what I'm talking about. Every problem demands a different logic. If I want to check, if I want to ask, how do you find the factorial of a number? You must find the logic. Then you should build as per your requirement, right? So every problem has a different criteria. You need to follow that. And in general, how do you know that? You need to practice some of the present and previous input bits of binary number. And what is this? And guys, this is one of the gate question. Guys, this is one of the gate question. They have given a machine, but you need to observe the functionality of the machine. Like they have given something like that, 0 1 1 0 1, something like that. And if I am looking at the sum of the present and previous input bits, look at that. 0, guys, this is the present bit. How to tell that, guys? 0 1 1 0 1. This is your input, and I want to produce the output, guys. 0 is the present bit. Who is previously there? Who is previously? Nobody. So you can assume 0. 1 is the present. This is the present, and previously nobody is there. So you get output 0. And guys, I know single bit is difficult, so they use 00 as an output. Input bit, the present bit. And next one, this one you are looking at. And what is this present bit? 1, but previous bit is 0. 0. So 1 plus 0 is a 1. So we will produce 0 1 as an output. And look at this one, 1. Who is the previous bit? 1. Because of this reason I was using 2 bits. 1 is the present and previous is 1. Previous is the 1. Remember that. Previous bit. This is the previous bit. Previous bit is very important. Is the previous bit 0 or 1? That makes a matter. In the previous problem, carry is there or not? Look at that. Carry is there or not? That you need to maintain the states. Here previous bit 0 or 1. So you require 2 states, guys, to remember that. If the previous bit is 1, go to that state. Previous bit 0, go to that state. So they will keep on understanding what was my previous bit. Okay, fine. Now 1 plus 1 is the 1, 0 is an output. Here single bit is not possible. This is the reason we have taken 2 bits to represent output. Now 0, and here addition is 0, present, previous is 1. 0 plus 1 is 1, so you can produce as 0 1. Right. Now this one, you look at the present and previous. 1 plus 0, and that's again 0 1. So you got the problem answer 0 0 0 1 1 0 and 0 1 and 0 1. This is the required output. This is input and this is output. Clear this point? Yeah, clear this point? Now it's not easy, guys, because you need to remember you are looking at the present bit, but how do you remember the previous? That along with the states only possible. Along with the states only possible, guys. Now I'm trying to design a machine for you, and I'm going to maintain 2 states. One is I'm assuming when I have previous bit is 0, you must come here, because internally I do that addition, remember that. And when I have a previous bit 1, please come here. Previous means we will understand slowly. Guys, look at now. Output and input both should be produced. When I am getting every state, two things you have to think. What happens on 0 and what happens on 1. What happens on 0, what happens on 1, because the deterministic machine, guys, this 0 is actually present. Previously there was no 0, right? There was no bit, so we can assume as a 0. Now 0 plus 0 is 0 is output. No doubt 0 is output, double 0 is an output. But where should I go? Should I go to previous bit 0, previous bit 1? You should go to previous bit 0, because this present become previous to the next bit. Clear this point? 0 0, because previously I had a 0, before that there was no input. And guys, previous to this one also 0, because I am coming from this state, means this 0 is there, and this 1 plus 0 is the 1. Output is 1, output is the 1. But should I go to this state or next state? You can remember the name. This is a capital A, this is a capital B. I should go to capital B, because this one become the next state. For the next bit, it will become 1 as the previous bit. Remember, here 1 by 1 comes. Everybody? No, here not 1, 0, 1 you should produce. Yes, 0, 1. But you should go to the next state, not the same state, Shubhasri, because for the next bit, 1 should be added. 1 should be added. This 1 will become the previous bit to the next bit. And guys, this 0, already look at that. This 0 we are looking at means already had a 1 previous bit. That is the reason we came here. 0 plus 1 is become 1 is the output. 1 is the output, means 0, 1. But this 0 become previous bit 0 to the next bit, remember that. And 1 means self loop, no doubt, because for the next bit this 1 become the previous bit. But output 1 plus 1 is become 1 0, 1 0. And this is what you require to produce. And this machine is given in the previous exam. This machine is given in the previous exam, and you need to understand. And they have removed the names. You don't have any name here. They just given this machine, guys. This is the A and this is the B. And tell me what is the output produced by this machine. And you take some input and observe what kind of output is coming. Right? So it's easily understandable if already designed. Because just you need to observe what is happening. And look at every option and match with your output. Right? Yeah. Clear this point? It's designed. Now another job is there. If somebody given the machine, then take the input and observe the output. Opposite you should do. Opposite you should do, remember. Okay guys. Now find the number of occurrences of 0 1. 0 1 in binary input. And this is homework for guys. I am just talking about if 0 1 appears. Produce something yourself. Produce like X. Otherwise produce Y. You decide it how to do that. Produce Y. If 0 1 appears, produce X. Example, input 1 0 1 0 0 1 0 1 1 1 0, and look at what is an output. And look at every time 0 1 comes, you must alert. 0 1 is your target. This is a 1 0 1. That means this one you produce Y. This 0 produce Y. When you see 0 1, produce Y. Again you will see 0 1. So what do you do? This Y you produce as X. Here you produce X, because you have seen 0 1. Now next start producing Y and again Y, and here you produce, again you have seen 0 1, produce X. I hope you understood the logic. How do we build? Because we decide how to build. And this 0 1 again we need to detect. So how do you do that? This 0 you produce Y, but this one you produce X. So number of X is nothing but number of 0 1s, and you have no more 0 1, right? So keep producing Y only. So this is the output, guys. This is the output. So Y Y X Y Y X Y X Y Y, and this is also Y. So how many number of X's are there? 3 x's, so that means 3 times 0 1 appeared. So 3 occurrences we can say that of 0 1s. This is how we build. You need to assume. So just whoever knows that how to detect ends with 0 1 problem. You know ends with 0 1 DFA, right? Take the same machine and you need to copy paste, that's all. Whoever knows how to design ends with 0 1 machine, 3 states required, design that. It's over, it's over. And if you want, I will help you very quickly. Ends with 0 1, guys. Let me help you. Ends with 0 1. Did you remember that? The machine, this ends with 0 1, right? And after that, if 0 comes, you come here, and 1 comes, come to the initial state, and any number of 1 stay there, and after 0 0 comes, wait there. And this is the machine for ends with 0 1. Now whoever comes to final, that means they have seen 0 1, that means produce x there. In other places produce a y. Over. Machine is over, guys. That's all you have to do. Q0, Q1, Q2. And final state not required. You can delete final state if you want it. Look at how to design the machine, guys. And this purely is the more machine, and this is the more machine. You can do milli machine if you want. How do you do construct the milli machine, guys? Just copy paste. Is that clear, everybody? Construct the DFA, and final state is your requirement. Whenever you reach final, put x there. Put x there means whenever you reach Q2, x will be produced. But by default, y is extra that is produced because default output for Murray machine. Okay, now let's look at the milli machine, how to design. Same Murray machine you take. Now I'm trying to help how to convert into milli machine. Copy paste the same machine, guys. Copy paste the same machine. No change in the machine. Only you are going to delete. Okay. Keep the 1 and keep 0 and keep 1. Keep 0 and then self loop 0, and then you have from here to here you have 1. So is that clear? Same diagram, no change. From every state 0 1 0 1 0 1. The output that you have inside the state, just put for incomings. So this y, whatever you have y here, this y you are going to send to the incomings, like 1 by y and 1 by y. That's all. And this y sent to the incomings, So 0 by y and 0 by y and 0 by y. And this x sent to the incomings, only 1 is coming, so put x there. So this is the milli machine, guys. It's a very easy to convert from the Murray machine. It's a very easy to convert from here. It's a very easy to convert. Okay, just send the output to the incoming edges. You will get the milli machine for the given Murray machine. That is the reason the Murray machine and milli machine are equivalent, because we can convert one to other. If you can do one of them, you can convert this machine to this machine and milli machine to Murray machine. Both are convertible from one to other. Clear? Come on, guys, clear this point. And I don't want you to practice many questions. Practice the previous year gate question, practice 5 or 10 problems from this model, and we will do some of the questions in the practicing marathon, and so that you will understand how to cope up with this kind of topics. But right now you must be good at understanding the concepts. Okay, just revise these 5 problems again, and with the theoretical concept you may understand it. Okay, now let me talk about the pumping lemma, guys. Before going for pumping lemma, let me help you. Whoever want to take the plus subscription, and guys, you will have the live classes interactively, and with every educator you can interact and you can learn from every educator. That is the most beneficial from the plus subscription. It's just like a Netflix. Once you take the subscription for 1 year, within 1 year you can go to any educator, you can go to any course, you can learn anything from Unacademy. Inside there is no restriction. What course you can enroll, what course you can learn, is everything is free. Only you should decide how many months, how many years you want to take the subscription. So that is the beauty of Unacademy. Entry restricted, but once you take an entry, then everything is unlimited number of times you can watch from anyone. So crash course, weekly test, doubt solving, so many benefits, and iconic, all the benefits of plus. Additionally, you will have a coach, one-to-one guidance with even every educator, and you will have a study planner, you will have study booster session, so many benefits for you for Iconic. To guarantee your rank, the Iconic plan is invented in Unacademy platform. There was no such plan in the world that like Iconic, never before. And guys, now let's talk about the pumping lemma. And this pumping lemma, most of the people they don't understand, is it for regular or non-regular? And remember that guys, pumping lemma for regular languages we take, but we use to prove non-regular also. Remember that pumping lemma is given for regular languages, how the regular languages will behave when the pumping lemma applied. And if the non-regular language is there, there is some case we can prove non-regular why it is. So let's talk about. And guys, if any language is regular, we are talking about regular concept, then there is a pumping length. This was a previous year GATE question. There was a pumping length which always depend on, this pumping length always depends on the minimum number of states or number of states in minimum DFA. Remember this point 2. This was a previous year GATE question. Number of states in minimum DFA. Right. So if I ask L is equal starting with A. Starting with A, how many states required? You require 3 states. So P has to be greater than or equal to 3. That means you can take 3 or you can take 4, you can take 5. It's your choice. It is your choice. If I am taking L is equal starting with AAA, you will have 5 states. You will have 5 states. Then P greater than or equal to 5 for this. The P is not 3, not 4. Remember that. It can be any value more than or equal to 3. That was the previous year GATE question. Which one of the following is possible to be P? So 3, 4, 5, 6, everything is possible. Right? You can delete 1, 2 option, but 3, 4, 5 you can choose, because for the first problem that P greater than or equal to 3. For the second problem 1, 2, 3, 4 impossible, but P has to start from 5. Okay, if you choose the pumping constant, that is a guarantee of the pumping. This is for given for infinite languages. Remember, for finite languages we don't apply. We say that okay, every regular language, every finite language is regular. Infinite language only we apply this pumping lemma. For every infinite language the pumping concept is applied. Remember that point. Finite languages pumping lemma cannot be applied. Just assume okay, regular language, every finite language is regular. So infinite languages we are talking about. For infinite languages we apply, and that too regular. And where if S is any string in A, the S is assumption and at least P. So length of S should be greater than or equal to P. This is, we assume length of W. Both are same. Length of the string that you take, basically. Length of any string you take. You can take any string from the given language. The W belongs to L, that is S belongs to L. And S may be divided into 3 pieces. Like if you have S and divide into 3 pieces, X, Y, Z, so that this X is a concatenation of X, Y, Z. Never forget, the concatenation sequence is very important. X, Y, Z, so that the pumping we apply at Y somehow. And that Y we are going to apply pumping, that we are going to repeat. And in case every pump is belongs to language, then we say that given L is regular, otherwise we need to understand the problem. So here the conditions are there. The length of the middle portion should be greater than 0, means Y should not be epsilon, and XY, length of XY, that first two parts must be less than or equal to P, so that that pumping can be guaranteed. Everybody, so let's look at what is the meaning of this. Guys, let's look at, suppose I have, let's say, containing EEE. I'm just taking it to help you. Containing EEE. And first you need to choose, step 1, choose a P. P is the constant. Pumping length. And this P, you know how many states required here? You require 4 states in minimum DF. Everybody knows that. So you must choose any P. Doesn't matter, 5, 6, 7, 8, you choose it. So P has to be greater than or equal to 4. So I choose P is equal, let's say 6. You can choose that. Okay, I've chosen it. And second, and choose a W. Choose S. Select string S. S means W basically. S that belongs to L, where length of S greater than or equal to P. So S I'm assuming, okay, I have chosen 6, right? So I am choosing 6 length, equal is satisfied. So I am choosing S is equal, S means W basically. String, okay, I am choosing, you know, A, B, triple A, B. This is a valid string, belongs to L, yes or no? 6 length belongs to L, belongs to L. Now, third point, you can divide into 3 parts, X, Y, Z, and assume here conditions are applied. Length of Y should be greater than 0, means I just assume something. So that it should not fail, guys. So Y, choose carefully, that should prove the language, remember that. B and Z I use triple AB, and this I choose A. And this constant XY length must be less than or equal to P. It means less than or equal to 6. H2 is less than or equal to 6. That's true. Now let's look at, did I prove the concept? The fourth point, for all I, xy power iz belongs to L, if and only if L is regular. But how do you know? Choose xyz carefully. You should choose S and divide into xyz that can prove regular. Remember that. Some selections may prove non-regular, but you should never do that, right? There is a case that can prove regular, that case you need to follow, and don't choose xyz that can prove non-regular. Never happens. Pumping lemma never be used to check the regularity, non-regularity. Remember, it is used to prove regular as the regular. Okay, alright. Now I'll talk about much theoretical points. What is important for gate? Now guys, is this true? The fourth one, is it true? Now x is what? A, and y is what? B power I, triple A B. Is it belongs to L for every I? Put I is equal 0, belongs to L. Yes or no? Just look at that. I is equal 1, still belongs to L because triple A always there. So every I, for all I, you can prove that it is belongs to L. I is equal 0, 1, 0 onwards, guys. Remember, I greater than or equal 0, I greater than or equal 0, I greater than or equal 0, we are able to prove that is the reason L is regular. But this is to prove regular, guys. To prove regular, we need to choose a pumping constant. That pumping constant depends on the number of states in minimum DFA, right? Depends on minimum DFA, and if it is non-regular, the concept is different. Guys. Now, proving regular languages, we have understood. What we have understood? You give L, that is regular. What we do? We do many things here to prove L is regular. We prove L is regular only. But to prove that, what we do, guys? Step 1, choose P. Second, choose a string S that is belongs to L and the length of S greater than or equal to P. And third, this is a constant, guys. Constant is very important. That P depends on number of states in minimum DFA. I am writing whole algorithm again to remember. And third one, divide S into 3 parts such that the length of y greater than 0 and length of xy that less than or equal to P, and divided is clear. And fourth point, for all I greater than or equal 0, xy power iz belongs to L, then only L is regular. This is the proof of regular language. But how can we use this proof for non-regular languages? That is the very important portion, guys. Yes. Is it clear? You can note down these notes, guys, because I'm not converting these days to the PDF. So you can note down these notes. How many pages are there? Hardly 5-6 pages you are not able to write. That's a very difficult part. If you keep on maintaining the notes, it will be very easy. Yeah. Alright. Now, how to prove non-regular? This is another fact. If you want to prove non-regular, we use a different strategy. Use a pumping lemma. Pumping lemma uses contradiction. Pumping lemma uses the proof by contradiction. It uses different approach now, not the same approach. It is pumping lemma basically works based on pigeonhole principle. This pumping lemma is actually note this power I, right, is depends on pigeonhole principle. So I'm just talking about the pumping lemma uses pigeonhole principle, and it uses now proof by contradiction to prove non-regularity. Now we can prove using contradiction for non-regulars. What is this concept, guys? It's just like you give non-regular, and it proves L. You give non-regular, it proves L is non-regular. But if you give regular, it can prove non-regular. Remember that. You have to give non-regular. It's not going to understand is it regular or non-regular. It just gives a proof. And what it does, and first step, assume L is regular. Second, it applies pumping lemma for regular concept. Then third point, there exists I such that x y power I z not in L. Okay, it assumes that contradiction occurred, because if it is a regular, every I should be in L, right? But it is not a regular, so contradiction occurs. So it assumes my assumption is wrong, so L is non-regular. That's what it assumes. This is the pumping lemma for non-regular, guys. Here, this was the algorithm for the previous one, but this algorithm is used internal to this proof. Previous algorithm entirely, this whole algorithm is going to be used for non-regular above this, guys. And this was we are trying to use, but here we got a contradiction. There exists I, we are not able to prove, which is belongs to L, so given L is non-regular. So let's look at one example to understand. One example, guys. Okay, here itself we understand. Okay, give me L is equal, let's say a power n, b power n. A power n, b power n. You have given this. Now I want to prove it is non-regular. So what I do? First step, I assume, okay, L is regular. Assume. This is assumption. This is assumption. But our assumption will fail if we choose carefully x, y, z. If you don't choose carefully, you may prove regular. Remember that. Second, that's algorithm. In that algorithm, we have a step 1. Choose P now. Guys, P. It's not a DFA, is impossible, right? So in general, you have to choose. Okay, choose P. I'm choosing 2n. Because here there is no number of states. In regular languages, you can decide the P, what is the minimum value of P. But here there is no minimum value of P, because infinite states if you design DFA. So be careful, guys. The P has to be chosen in general now. P is equal to n, because a power n, b power n, if you look at that, it's 2n. And I'm going to choose a string. Choose S, so that its length is, then I'm going to choose, okay, length is 2n, that matches with a power n, b power n. Right, now in the third step here itself, I'm going to divide a power n, b power n into 3 parts. Okay, I'm going to divide, so I'll guarantee here a is there. So here a power n minus 1 and b power n, because a is greater than 0 length, right? Now that fourth step inside here, now I'm going to prove that, I'm trying that for all I is really x, y power I, z belongs to L. I'm trying that, but when I'm doing it, a power n minus 1, a power I, b power n, is it belongs to L always? Okay, we got a contradiction. We got third step, that is there exists I. Which I we can do that? Okay, I is equal 0, you can do. I is equal 0, a power n minus 1, b power n not belongs to L. Contradiction occurred. That is the fourth one. We have got contradiction, because it's not belongs to L all the time. So it is given L is non-regular. This is how we prove, because our assumption is wrong. Clear this point? We are going to use the proof of regular to prove a non-regular using contradiction. The second point is actually proof of regular. The second point, whatever we did, is the proof of regular. Proof for regular language. proof for regular language. We are using for non-regular with the help of contradiction. With the help of, this is whole box is proof by contradiction. Clear this point? So this is how we can prove. And guys, one point you need to remember, the pumping lemma is not used to verify whether regular or not. Pumping lemma cannot be used to check whether given language is regular or not. We don't know that way. Given language is regular or not, we don't do ever. What we do instead of that? Pumping lemma cannot be used. Pumping lemma used to prove regular as a regular, that's all. Pumping lemma is used to prove regulars. Pumping lemma is used to prove non-regulars, that's all. Don't ask is it regular or not, it can't answer it. Using, this is the second one, using contradiction. But pumping lemma cannot be used to verify whether given language is regular or not. Given language we never know what is it. Then how can you assume, should I use a pumping lemma directly or should I use a contradiction? You don't know. There are two proofs here. Pumping lemma for regular is different. Pumping lemma for non-regular using contradiction. There are two proofs here. So both of them should be applied different way. If you are giving input is regular, then your focus is on direct proof. But if you are giving non-regular, you should focus on contradiction. So given language decides what we use. So, and we never check for regular or non-regular. We do input is given regular, then we will show why regular. That's all. Why L is regular. If given L is regular, why L is regular. If given L is non-regular, then we will show that why it is non-regular. Why L is non-regular, that's all. But we never check given language, unknown language is regular or not. We never use this to prove, to verify, not to prove, verify whether given language is regular or not. Okay, this is the most important point. So today in this session, I hope you remembered pumping lemma. Remember the words satisfies regular. That is the proof we have used. But pumping lemma we can use to prove regulars directly, and we can use to prove non-regulars but not directly, to prove non-regulars using contradiction, to prove non-regulars using contradiction. And guys, watch this video and compare with anybody else, and you will understand what you are learning from other videos and this video, and you will definitely look at the difference. How do you learn the pumping lemma, and it's going to be different from other lectures that you see online, and definitely you will see something interesting in this video. I hope this video will helpful for you. And what is pumping lemma for regular languages? Pumping lemma how to use to prove non-regular languages. Pumping lemma for regular only we have, but we can use for regulars if we want directly, and you can also use for non-regulars but not directly using contradiction. So this is how we use for both the places, but we don't verify given unknown language. So today we have learned 2 points. Yeah, finite automata with output, a Lemma Machine and Mallesham Machine, and another one pumping lemma for regular languages. Right. So these are less important for GATE, but never ignore these 2 topics because easy questions were already asked in the exam. And we are going to practice in coming Saturday. So what kind of questions we have already. And guys, do not forget to like this session, and please follow me on Unacademy, and never forget the DEVALIVE referral code to refer my code to your friends and your juniors or any known person. If you want to refer, you can do this, and that will benefit me indirectly. And this is our Telegram channel. You can subscribe to get daily updates, and these are free YouTube channels from top educators from Unacademy. Please share with your friends to any engineering student, and thank you so much, and please like this session and also share and subscribe. Thank you so much for attending today's session, guys. See you in the next class. Bye bye, take care.